Now we're going to look at a problem dealing with how do we calculate the amount of product that can be produced in a chemical reaction, how can we predict or calculate the amount of reagent we would need to produce a certain amount of product, all these types of calculations. And we've looked already at a fairly straightforward, basic type stoichiometry problem, but now we're going to look at one that's a little more complex. It's going to be the same thing, they're going to be the same steps, except we're going to have to add a couple things onto it. I always talk about these types of problems in terms of a Christmas tree. I always think of them like a Christmas tree. Whereas stoichiometry is sort of the tree itself. And that's the part where we use the chemical reaction and the coefficients in the chemical reaction to calculate the molar ratios produced produced or reacted in a chemical reaction. The things like converting between grams and moles, or using the ideal gas law, or molarity, or and things like that, those are sort of like the ornaments. They go on that tree and they're part of it and they make it look nice and pretty, but in reality, it's just a plain old stoichiometry problem. So let's go through and work this one. It's talking about 856 grams of glucose. We've got our glucose, our C6H12O6, and we've got 856 grams of glucose. So now we have this glucose. We want to know what mass of carbon dioxide we can produce whenever we react this completely with oxygen. Now notice it doesn't tell us anything about the amount of oxygen here, so we're assuming that there's excess. There's lots and lots of oxygen, enough such that this glucose is going to run out before the oxygen does. So we're going to find later we have a special name for that, and that the glucose will be what's called a limiting reagent. But we're going to get to that in a day or two. So now we've got this 856 grams. We know that one glucose reacts with 6 oxygen molecules to produce 6 carbon dioxide and 6 water molecules. We also know those are molar ratios. So 1 mole of this to 6 moles of this to 6 moles of this to 6 moles of this. So we have a molar ratio, but we do not have a gram ratio. So we have to convert this grams to moles of glucose. And I will tell you that I already have the molar mass. We need to have grams of C6H12O6 glucose here on the bottom. And we want to know how many grams are in 1 mole of glucose. So we calculate the molar mass by adding up all the atomic masses, and that's something you should be getting pretty comfortable with now. And I've already calculated that as 180.12 grams. That's how many grams we would need to have 1 mole of those molecules. And we need 180 grams. So the grams cross out. We now would have, if we would stop at this point, we would have calculated how many moles of glucose we have in those 856 grams. Now is where the stoichiometry step comes in. What we've done so far, that's like the ornament on the Christmas tree. This part is like the Christmas tree itself. It's the actual stoichiometry. How many moles of glucose? Well, I look at the coefficient, 1 mole of glucose. Put that in the bottom so that the moles will cross out. And I want to figure out something about carbon dioxide, in particular the mass. So I want to know first, how many moles of carbon dioxide can I produce when I react this number of moles of glucose? So 1 glucose to 6 carbon dioxide, just taking the coefficients from the balanced chemical equation. And if I stop, I would have calculated how many moles of carbon dioxide I can produce from the 856 grams. But that is not where we want to stop. We want to figure out what the mass of carbon dioxide would be. So we need to know the molar mass of that carbon dioxide. And we know that 1 mole of CO2, or at least we know because you've either seen it in the problem or you've seen it here on the board, we know that 1 mole of carbon dioxide is 44.01 grams of carbon dioxide. So the moles again cross out. I work it out that way, and I'm left with grams of carbon dioxide. Plug it into your calculator, you should get 1.25 times 10 to the third grams of carbon dioxide produced. And that will be our answer for this problem. Now what you're going to see is that we're going to do problems like this over and over and over again throughout this semester, and not just this semester. This type of stoichiometric calculation will stay with you in every chemistry course that you take. Even organic chemistry, which doesn't tend to be as quantitative as general chemistry is, you will have to do stoichiometric calculations to determine percent yield, theoretical yield, things like that for your different chemical reactions that you perform. So a very important calculation. It very much behooves you to understand how to work a calculation like this. So if you have questions or you're not quite sure, it still isn't clear how to do a problem like this, please try a couple practice ones, see if you can figure out on your own. The best form of learning comes from figuring things out by doing them over and over again, repetitive nature. But also the best learning comes from doing something wrong and examining it to figure out how to do it right. So if that doesn't work, then why don't you let me know? I'll be able to come and help you figure this problem out. Okay?